Hello dear students, this is your GURUDEB. Today we'll be discussing about some important trigonometric identities. So to start with, let's take a problem which is tan theta by 2 into 1 plus sec theta into 1 plus sec 2 theta. In this way, this product continues up to 1 plus sec 2 to the power n theta. So let us take this to be some function of theta, and let's see that how some trigonometric identities will help us to reduce this particular product. So here, if you identify and cut out the first two product, that is, if I consider the first two product, tan theta by 2 into 1 plus sec theta, so we can see that this can be written as, if we convert tan theta by 2 to sin theta by 2 by cos theta by 2, and let us write sec theta as 1 by cos theta. So on simplifying, this will come out to be sin theta by 2 divided by cos theta by 2 into, on simplifying, the numerator will become 1 plus cos theta divided by cos theta. And as you know from submultiple angle, 1 plus cos theta can be written as 2 cos square theta by 2. So you can easily see that 1 cos theta by 2 will be cancelled out from the denominator, so this will be cancelled out. So we'll be having the value to be 2 sin theta by 2 cos theta by 2 divided by cos theta. And now the numerator will be clubbed to give you sin theta. Okay, so the total packet will be sin theta divided by cos theta, so it will going to give you tan theta. So this becomes an identity like this product tan theta by 2 into 1 plus sec theta. This is nothing but, this comes out to be tan theta. So we can highlight this particular identity here. So that is tan theta by 2 into 1 plus sec theta. It comes out to be tan theta. Now you can see that this bracket, I mean this whole thing, will be easily replaced by tan theta. So in place of this rectangle, tan theta will come. So it will become tan theta into 1 plus sec 2 theta. Now we can see that the identity that we have just derived, so this can be recursively used to reduce this particular series, because you see that since this is an identity that we have just derived, so in this identity we can replace theta by any expression of theta. Like if I replace theta by 2 theta, okay, if I replace theta by 2 theta, you can easily see that this is going to be tan theta into 1 plus sec 2 theta, and automatically the result will become equal to tan 2 theta, because we have replaced theta by 2 theta. So you can see that this thing can be used in place of this particular, because this quantity will become tan theta, so that tan theta will be clubbed with 1 plus sec 2 theta. So this will be again equal to tan 2 theta. So we can easily say that this thing is going to be tan 2 theta, and then this tan 2 theta is going to get clubbed with the next particular factor, that is 1 plus sec 2 square theta, and this is going to give you tan 2 square theta. So in this way we can see that the series is basically getting reduced because the terms are gradually getting consumed. Okay, this particular thing becomes tan theta, then tan theta into 1 plus sec 2 theta become tan 2 theta, then tan 2 theta into 1 plus sec 2 square theta will become tan 2 square theta. So in this way all the terms are getting consumed, and you can see that finally for the very last term, that is 1 plus sec 2 to the power n theta, we can write down the reduced form of the function to be equivalent to, so it's going to be f theta equal to, so for the last bracket is 1 plus sec 2 to the power n theta, so that will have its partner, you can see like 1 plus sec theta. If it is theta, then the partner is tan theta by 2. So if the angle is theta, the partner have an angle theta by 2. So if we have the last particular factor 1 plus sec 2 to the power n theta, in that case its partner is going to be tan 2 to the power n minus 1 theta, and finally they will be clubbed to give us the most compact result, that is tan 2 to the power n theta. Okay, so you can see that this product can very easily be reduced to tan 2 to the power n theta. So this is going to be your final answer for the simplification of this problem. So basically you see that the identity that we have derived initially can be recursively used by replacing theta by 2 theta, then again theta by 2 theta, to gradually reduce the terms in the series. Let us take a similar problem, okay, where the terms will get consumed like in this particular question. So let us consider a product which is named P, and the product is cos x into cos 2x into cos 2 square x into cos 2 cube x, and this thing continues up to cos 2 to the power n minus 1x. So you can easily see that we are starting from 1 into x, that is we can say 2 to the power 0 into x. So this quantity can be actually written as 2 to the power 0. So 2 to the power 0, then 2 to the power 1, 2 to the power 2, 2 to the power 3, up to 2 to the power n minus 1. So starting from 2 to the power 0 up to 2 to the power n minus 1, we can see that total n number of factors are there. So n number of cosine components are there, and we need to come out with a very compact result for this particular product containing n terms. So to simplify this series, we can start by multiplying both the side with a factor that is 2 sin x. Okay, so let us multiply both the side by 2 sin x. So that 2 sin x will be clubbed with this particular cos x to give us a compact result according to your multiple angle. So 2 sin x into cos x, they will be clubbed, keeping the rest of the terms as it is, no change in the rest of the terms. Now you can see that this 2 sin x into cos x, this will basically be nothing but sin 2x, and you can see that for this particular sin 2x, the very next cos 2x can be clubbed with it. So sin 2x into cos 2x, then cos 2 square x, and the rest of the terms. Now sin 2x and cos 2x, they will be clubbed using multiple angle, but for that we need a 2 before sin 2x, so that it will become 2 sin a cos a. So that 2 can be easily provided by multiplying a 2 here on the LHS. So we can easily write it as 2 square sin x into p, and that extra 2 will be balanced here, so that 2 sin 2x into cos 2x becomes sin 2 square x. And again you can see that sin 2 square x will be clubbed with the next cos 2 square x. Okay, and again for that we need a 2, So let us again multiply the LHS by another 2, so it will become 2 cube sine x into p. So in this way you can see that the terms of the series are gradually getting consumed. Okay, the terms are getting consumed and the length of the series is getting reduced. Okay, so in this way finally you can see for the very last cosine term, so cosine 2 to the power n minus 1x, that is the nth term for the very last nth cosine component, we need to multiply a 2 for the very last time, and that will be the nth time. So if I continue this pattern, and finally we'll be having 2 to the power n sine x into p, so that will become equal to, this cosine term will be clubbed with the previous sine term, so that will be 2 sine 2 to the power n minus 1x into cosine 2 to the power n minus 1x, and they finally will give us a result that is sine of the double of the angle. So double of this particular angle is nothing but sine 2 to the power nx. So now we can very easily get a simplified result for p. So p comes out to be sine 2 to the power nx divided by 2 to the power n into sine x. So we can say that this is our final result of the product. Okay, so this is going to be the answer. So for the product p, we have come out with an answer which is sine 2 to the power nx divided by 2 to the power n sine x. Now let's see that how this result that we have just derived can be used to create another very important identity in trigonometry, which often comes as a problem to us. Okay, so let's see that this identity, how it can be creatively used. So let us write down this result that we have just derived. And the result was cos x into cos 2x into cos 2 squared x, in this way up to cos 2 to the power n minus 1x equals, the result we can just copy. The result comes out to be sine 2 to the power nx divided by 2 to the power n sine x. So this result we have just derived. Now from here we'll be creating another identity. Let us follow a process, that is suppose taking log on both sides. Taking log on both sides, it will become log of cos x plus log of cos 2x. You can see that I'm using the log property on the left hand side, because if I operate log on both the sides, so log of this total thing is equal to log of the right hand side. Now in the LHS you can see that log of it is product of n number of quantity, so it will be added after operating log. So it will become log cos x plus log cos 2x in this way up to log of cos 2 to the power n minus 1x, and that will be equivalent to taking the log on the right hand side. So the right hand side is log of a by b, so that can be written as log of a, okay, log of the numerator minus log of 2 to the power n minus log of sine x. Okay, log property is used. Now after taking log, we can see that our left hand side is a function of x and our right hand side is also a function of x. So since the two functions are identical, so we can differentiate them and their derivative should also become identical. So if we differentiate with respect to x, if we differentiate both the sides with respect to x, then you can see that the derivative of log of cos x, for doing the derivative of log of cos x, will follow the chain rule. So first we'll be differentiating the outside function, that is the log function. So it will result 1 by cos x, okay, because you know that the derivative of log x is 1 by x. So the derivative of log of cos x will become 1 by cos x, and then we need to go for the inside function, that is cos x. So we'll be differentiating cos x to give us a result that is minus sin x. So you can see that the derivative of log of cos x is coming out to be minus tan x. Okay, I've used the chain rule to differentiate the first function. So the derivative of first component becomes equal to minus tan x. Similarly, for the next one, it will become minus tan 2x, okay, because the angle has become 2x. But now you see that this 2 will come into picture, because for the derivative of 2x, this 2 will come out. The derivative of 2x will give you 2, so 2 will come here. Then similarly, the next one will become 2 square tan 2 square x, okay. So in this way it will continue up to the last logarithm, which will give us a result that is 2 to the power n minus 1 tan 2 to the power n minus 1 x, and that will be equivalent to the derivative of log of sine 2 to the power nx. So again apply the chain rule. Log of sine 2 to the power nx, using chain rule, it will give you 1 by sine 2 to the power nx into the derivative of sine 2 to the power nx, that is cos 2 to the power nx, into the derivative of 2 to the power nx, which is nothing but 2 to the power n. So everything will be multiplied. So you can see that it is coming out to be 2 to the power n into cos by sine, that is cot. So 2 to the power n into cot 2 to the power n x. Then you can see that log 2 to the power n, this is the constant quantity, so on differentiating this should become 0. And finally we are having log of sine x, so the derivative should become 1 by sine x into the derivative of sine x, which is nothing but cos x. So this can be written as cot x. So you can see that after differentiating we are getting another identity which is very important. That identity can be written as like let us take this tan cot x term on the LHS and bring all the other quantity in the RHS. Okay, so we can write the final identity as tan x plus 2 tan 2x plus 2 square tan 2 square x. So this thing continues up to this particular term, that is 2 to the power n minus 1 tan 2 to the power n minus 1 x, and this will be added with it, plus 2 to the power n cot 2 to the power n x. This quantity will be equivalent to this cot x will go on the other side, and so let us write cot x. So this is the identity that we have derived from the previous result. So this is another very important identity problem which is usually asked in different exams, competitive exams as well as your school exams. Okay, so we can note this down to be an important identity. And in this result you can see that whatever with the value of n, the result is every time coming out to be cot x. So the result is independent of n. we can have any number of terms, we can have infinite number of terms in this series. The result is not going to change, the result is still going to be cortex. So we can say that the result is independent of n. So it is independent of the number of terms in the series. So thank you for watching this particular video. So you can email me or you can contact me if you are having any doubt, and you can also request me if you need any particular type of discussion on this channel, and you can subscribe on YouTube and like us on Facebook so that you regularly get the video updates if any new videos are getting uploaded. Thank you.